All right, so the first thing that I want to do is those of you that are in the classroom, you've received your quizzes back from yesterday and today's Unit 3. Is there anything specific that we want to talk about related to any of that before we get into just more generic things? Clayton, you had something?
What's actually happening with the atom in ionization energy versus, say, atomic size?
Okay, so if we're looking at ionization energy as an overall kind of construct here, what we want to think about is if this is our atom here, or if this is our nucleus, ionization energy would be, let's say we've got electrons here on our nucleus, surrounding our nucleus here. How much energy input would it take to strike one of those electrons and force it to completely leave the atom? That's what ionization energy is. How much energy would it take for an atom to lose one of its electrons? And the thing that we have to look at and kind of consider here is that there's obviously going to be some relationships between the size of the atom and the ability to ionize it. We talked about this in class. The closer the electrons are to the nucleus, the more difficult it's going to be for them to break away from the nucleus because they're going to be held more tightly. And so if you can imagine this atom where we only had the 2 electrons in this first energy level, and we compare it to, say, this atom with a considerably larger nucleus, but also considerably larger atom as well. Don't make fun of my crappy circles. They're my crappy circles. But if we're looking at trying to ionize that electron there, which is considerably further away from the nucleus, I think it wouldn't take much of a logical leap for any of us to go, oh yeah, that one's further away. So it's not going to require nearly as much energy to get rid of it. And so when it comes to ionization energy, that's the first thing that we're going to look for is if I'm trying to compare 2 different substances, 2 different species, which one's bigger? Because the bigger one's going to be easier to ionize. Where we run into problems is when we have that scenario where we can't just look at size. Those are those configuration anomalies that we talked about. The half-filled p orbital, in group 15, the completely filled s orbital in group 2. Those 2 groups stand out a little bit differently because they are a little bit different in terms of they've got a filled sublevel, and a filled sublevel is a little bit more stable than one that's partially filled. So that's why we see, even though beryllium is bigger than boron, it's harder to ionize. even though nitrogen is bigger than oxygen, it's harder to ionize. And it comes down to, well, not just how many electrons are there, but where are those electrons? So long as you are avoiding those situations, it really does just come down to size. Bigger means that the electrons are further away. If they're further away, they're going to be easier to remove. All right, anything further with that concept? Right, any other specific questions that we wanted to cover here? Okay, that's okay. We're still somewhat early in the process. The exam's not until Monday. Most of you probably haven't really gotten to that point, especially since we just did the last quiz for that either literally just hours ago or yesterday afternoon. So your head's probably not in that frame for studying for an exam yet, but it needs to get there soon. Any of my past students will tell you studying the night before or the day of the exam is not going to be something that is going to work out well for you. You want to be studying in little bits and little pieces over the next 3 or 4 days. Now, part of what we've been doing in class all along has kind of been training you to do that anyway. Your homework assignments are all designed where you're supposed to be spending 20, 30 minutes just kind of picking up the pieces from the last lecture. That's really all I'm asking you to do as we get into Friday and Saturday, and then probably a bigger chunk of time on Sunday. Start going through these concepts, start going through these chapters and picking up on, okay, well, this is something I'm good at. This is something I'm not as good at. What can I do to get better? What kinds of things do I need to improve upon? And that's really where these practice exams come in pretty handy as well. Has anyone looked at the practice test yet? Okay. Any questions off of that practice test? The quantization of which? Oh. This one? Okay, so question 16 in the practice test. Which of these occurs only in discrete or quantized increments? Well, remember, quantization means that we have to have some kind of a non-continuous value. And so while your speedometer might only give you a readout to the ones place, you know that, when it says you're going 70 miles an hour, there's a good chance that you're going something other than 70 miles an hour. Maybe you're going 70.4, maybe you're going 69.5. You'd be going in a range of values there. And even the range has ranges within it. Same thing with altitude. How high up the plane is, we'll give you an estimate. We'll tell you that we're at 30,000 feet, but we know that that's an estimate. It's probably somewhere along the lines of differently. Same thing with time. We can split time up into seconds, into milliseconds, into microseconds, into nanoseconds. We can keep splitting time infinitely depending upon what it is that we're measuring. The level of water in the sink, well, is it this high, or 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 is it somewhere above or below? These are all continuous amounts. Money, however, is not continuous. There is a discrete end to money, the penny. You can't get a smaller value of money other than 1 cent, at least not in terms of actual coin money. Now, what your bank tells you is your interest rate and how much money that turns into on a quarterly basis. Yeah, they get into fractions and all that stuff there. But if you walk into the bank tomorrow and say, hey, I want 35 and a quarter cents, they're going to look at you like you got something going on. Because there's no such thing as a quarter cent. But certainly, yeah, I want to go into the bank and come out with $100. They're going to be able to give me $100. They're going to be able to give me any amount of money I want down to the cent. But that's where it stops. And that's why it's not continuous. There's a discrete end to money. We call it the penny. Any other questions from the practice test for those of you that have seen it? Right, then for those of you that are in my Chem 187, what I'm going to tell you to do next is going to be no surprise. So what I did for this is I took another one of my exams, well, a more recent exam, and I turned it into an activity. And what we're going to do is we're going to go through the activity kind of together here, and it'll give you a chance to ask some more questions and do that kind of thing. So once I get this loaded up, right? So if you're on Zoom, you can join this as well. You need to go to joinmyquiz.com, either on your phone or on your laptop, whatever browser you have. It's going to ask you for a game code. Put in this 6-digit code there, 640950, and that'll get you into the game, and then we'll get started. Okay, so the question was, according to law of definite proportions, which of these is true? The correct answer here was this second one. Different samples of the same compound are going to have the same chemical makeup, the same ratio of one element to the other. Now, the other options here were all valid laws in some kind of way. But this was the only one that was actually describing the law of definite proportions. So in the exam, there is going to be a combination of multiple choice and free response. And this is going to kind of mimic that as well. Most of the stuff that you're going to find in the multiple choice section are going to be questions like this, where I'm asking you to either define something or relate some kind of a concept to something or any number of things. But it's going to be definitely in that non-calculation kind of mode. All right, by definition, pure substances are either going to be compounds or elements. So the gold, the oxygen, those are both elements. The water vapor, the dry ice, those are both compounds. Carbonated water would be a mixture. It's a mixture of water and gas, carbon dioxide. Okay, so most of you got this. Elements cannot be separated into simpler substances chemically. They are as simple as they get. And so some of the trick kind of answers in here, yes, most elements do exist as atoms, but we talked about some that do exist as molecules. The 7 diatomics, hydrogen, nitrogen, oxygen, fluorine, and the other halogens. But elements can't be compounds also. That's the very definition of a compound. It has to have more than one element in it. And we would hope that different samples of elements don't have different chemical properties, because that would kind of throw things off pretty bad for us. If we're looking for chemical properties, we have to be looking for something having to do with chemical reactions. Other than reacting with oxygen, all these other things can be observed without actually doing anything to the iron. I don't need to react the iron to observe its density, or to observe that it's magnetic, or to observe its conductivity. But if I want to see if it reacts with oxygen, I've got to put it in the presence of oxygen and see what happens. Okay, not a surprise, there's more of a spread here. Logic would dictate that the answer to this question is either going to be the one with the highest density or the one with the lowest density. If you picked ice, you probably didn't see that cocoa butter was just slightly less dense. Now, remember that density shows an inverse relationship between the mass and the volume. If I've got a high mass and a high volume, density kind of evens itself out. If my volume increases, then my density is going to have to decrease, and vice versa. So if I have equal masses of all of these, the one with the greatest volume is going to be the one that takes up the most space, the one that has the lowest density, the cocoa butter. Okay, here's where we got to make sure we understand the question. For approximately equal masses, we're looking inside the nucleus. The proton and the neutron have roughly even mass. The electron has virtually no mass next to either of those two. If we're looking at charge, the proton and the electron have roughly the same charge, just in opposite fields, positive versus negative. Formatting there did not come out to best effect there. Those are both superscripts. So we're talking about carbon 12 and carbon 13. And so isotopes, yes. I've got two elements. The only difference between them is their mass number. That's the very definition of an isotope. Let me Well, that's what I get for not proofreading this. Okay. We know this is oxygen. So what else do we know about it? So as oxygen, it's going to have 8 protons. So everything except for this one is a possibility still. With a mass number of 16, we know that we're going to have 8 neutrons as well. So that actually eliminates the other 2 options. And with a charge of -2, -2s is protons minus electrons. So we should have 10 electrons. So the correct answer here is none of them. You know, they tell you when you use AI to do things to help you go faster, that you should always proofread the AI before you present it in front of anybody. It looks like I've been caught. So the correct answer here, and obviously I'm not having AI make my exam or my key on Monday. So you'll get the full direction here. I just wanted to do something quickly. And rather than just go through the practice test piece by piece, this is a little bit more interactive. So I will deal with these embarrassments, especially since they're embarrassing me and not you. Remember, groups on the periodic table are also known as families. The reason they have that is because they often share a lot of common characteristics. So when you have a question like this, you want to look for elements that are in the same vertical column, the same group. Calcium and strontium are both alkaline earth metals, so we would expect them to have properties similar to other alkaline earth metals. Moderate water reactivity, reasonably slow air reactivity, pretty reactive with acids, that kind of thing. Quizzes is funny. It is looking for an exact answer. So to help you out a little bit, you do not need a unit. Make sure that you round it to 2 decimal places so that you don't get accidentally marked for an incorrect response when you had a correct one all along. All right, in the interest of time, I'm going to shut down the question here in about 5 seconds. Okay, so the key here is we had 2 chromiums and 3 oxygens. So the 2 chromiums would have been 104 grams. The 3 oxygens would have been 48 grams. I put that together, I get 152.00 grams. And so if you're in that red column, hopefully it's because you forgot about the 2 decimal places part and not because you made some other kind of mistake with the formula. Now this one I'm interested to see the results in because I remember proofing this and I remember seeing this one being wrong initially. I'm hoping I remembered to edit it before I saved it this afternoon, but we'll find out in a minute. Yeah, it's wrong. All right, question is which one's correct? We're kind of all over the place. So we got a chance to make a pretty good guess here. If I'm in a subshell, I have to automatically be in the same shell, right? So which quantum number is that? Principal, N. Okay, so we know it has to be principal. It's also the same subshell. Which quantum number is that? Angular momentum, L. So those two have to be the same if I'm in the same orbital group. Can I go further than that? No. Because after that, I'd be talking about an individual orbital within that subshell. And that's not what's being described here. So if I'm talking about orbitals within a subshell, I'm going to have the same principal quantum number N. I'm going to have the same angular momentum quantum number L. I'm going to have those 2 things. Beyond that, now we're getting into a bit more specific kinds of information. So this is wrong. This one is right. And it's a good thing we're not keeping score anyway. Okay, this one is keyed correctly. Why is it this group? So we did a problem similar to this in class, where we were looking for kind of the same information. What kind of quantum number sets go together and what kind don't. And so the thing that we always want to look for in these is, first of all, we want to look for obvious mistakes. Things like spin quantum numbers that are anything but plus or minus a half, or negative energy levels, that kind of stuff. But if we don't have that, then the next thing we want to look for is, where is it breaking the rules? And if we look closely here, what we can see is that if this is the first energy level, and we're talking about the 1s orbital right here, you can't have a magnetic quantum number of -1 if it's an s orbital. The only thing that you can have is an angular quantum, a magnetic quantum number of 0, because there's only one possible orientation for s. It's a sphere. It goes in all 3 dimensions all the time. Everything else is within boundaries. L has to be within n-1 of n, so 3 to 2, that's okay. M sub L has to be within -L and positive L, so that all works out for all of these as well. We really just get down to, in that first one, we broke the rule with the magnetic quantum number. If this question looks familiar, it's basically the reverse of what you had to do on the quiz. In the quiz, we gave you the orbital designation. You had to give us the quantum numbers. Basically, we're asking you to do the opposite here. If n is equal to 3, then we know that we're dealing with the third energy level. L is equal to 2 should tell us D. This is the 3D sublevel. So 3D should be the correct answer. Most of you got that. Good. Atomic radius, this is a relatively easy trend to follow along with. What we should be looking at first is, we want to look at energy levels, how many there are. Fewest is going to make the smallest, the largest is going to be the most. And then nuclear size, how many protons are in the nucleus. So for calcium, we're looking at 4 energy levels. For rubidium, 5. For sodium, 3. For aluminum, 3. And for chlorine, 3. So we can automatically wipe out calcium and rubidium. They're too big. They have too many energy levels to be the correct answer here. From here, it comes down to a matter of protons. Sodium has 11. Aluminum has 13. Chlorine has 17. More protons means more electronic pull. Again, bring those electrons in further. So this one, chlorine, is going to be the smallest. All right, I'm actually going to skip this one. And not for anything, most of you on the quiz did really well with electron configurations. We've got about 20 minutes left. I'd rather spend our time on the stuff we didn't do as well with. Just to avoid any confusion here, increasing order means we're going from small to big. We're going to use the same kind of logic. So again, start with energy levels. So sulfur has 3, fluorine has 2, silicon has 3, potassium has 4, and magnesium has 3. So we already know the bookends here. Fluorine is going to be the smallest, potassium is going to be the biggest, and right away we can eliminate this option and this option because they don't follow the bookends at least. From here, it comes down to, again, what is my atomic number? So for sulfur, it's 16. For silicon, it's 14. And for magnesium, it's 12. The bigger the number, the smaller it's going to be. So sulfur would be next, followed by silicon, followed by magnesium. That gives us the second option as the correct answer. And most of you got that. Good job. Right. There are 5 of these questions. We're going to do a couple of them, just some quick hitters here. The majority here is correct. All we are doing is separating the components of a mixture. Salt water, seawater is a mixture. To separate from the water from the salt, we would just have to boil off the water. That's a physical process. We're getting the water to change phase. The solid isn't changing phase at all. It just stays behind. Basically, same scenario. We've got a mixture of liquids this time. We're just removing one of the components of that from the others. So it's still physical. Same ratio each time. Okay, this is chemical. Reason it's chemical is because we're not starting with a mixture of things. We're starting with a compound, mercury 2 oxide, and we are heating it to draw off the mercury from the mercury oxide. We've got a compound turning into an element. That's a chemical change. We went from HGO to Hg. This is a decomposition reaction. Same exact idea. We've got a decomposition reaction happening here as well. Iron 3 oxide, Fe2O3, is being warmed up to get the O2 away from the iron 3 oxide. All right. Unless it's keyed in wrong. Yeah, we're all good here. Yeah, this is an exercise in density. When you make salad dressing, you're not doing any sort of chemical reactions. You're literally just mixing things together and getting them to kind of be together for long enough for you to pour it over your salad. You let it sit on the counter, all the components separate based on their densities. You're back to exactly where you started again. Okay, I put this one on here. This is an example of probably the most missed question on the Unit 2 quiz. Converting between compounds and elements, and having to use Avogadro's number properly. This might be the last question we do, hopefully not, but I want to make sure that we get through this one because, again, more people missed that question on the Unit 2 quiz than any other question. All right, I know not everybody's in, but let's go ahead and try to make some sense of this. And so, conversation I was having in the back of the room. What do you do if you just come to a question like this and you go, I have no idea what you're asking me. I don't know what to do. I don't know the first thing to do. I don't know the first step. Hopefully, you can at least recognize that there are some things here that you can connect together. I've got a molar mass and I've got a mass of substance. If anything else, I can turn that mass into moles using the molar mass. And that is the basis of partial credit. This is why you never should leave a question blank unless you are looking at the clock and saying, oh, I've got 2 minutes left. Guess I'm not getting all of this done. But unless the clock's got zeros on it, or in our case, a 50 on it, you've got time to at least put together something that makes sense. And so writing down something, even if it's not the full correct answer, if it's part of the way to the correct answer, if it's one of the steps that gets you to the correct answer, that's going to earn you something as far as partial credit goes. And it doesn't matter if we're talking about a quiz situation or our exam on Monday. That's how that system works. So our first step here needs to be, we're taking the 1.5 grams of the antirin chloride, and no, I'm not going to write that out. I'm going to abbreviate because that's way too long of a compound to try to write out. My first step is to convert this into moles. That's what the molar mass they give me is 4. Now, the next step, this is where a lot of you would have ran into trouble in the Unit 2 quiz, where a lot of you are running into trouble now. I don't need moles of antirin chloride. I need carbon atoms. Well, 2 approaches that you can take to this. I can either turn the antirin chloride into carbon now in this step, or I can do it in the next step, and I turn my compound into molecules at this stage. It really doesn't matter. Me personally, I like breaking it apart beforehand. In that graphic organizer I gave you, that's what it tells you to do too. Take your moles of compound and turn it into moles of elements. This is where the chemical formula comes in. Every mole of antirin chloride has 27 moles of carbon in it. Where did that 27 come from? It came from the chemical formula. Last step, I need to turn the moles of carbon into atoms. Here's where Avogadro's number comes in. Lucky for you, I know some of you have had real difficulties trying to memorize this number. It is going to be on the equation sheet for Monday. So I figured if the ACS is not going to deprive you of it, I shouldn't either. So it's in your final exam information. It'll be in your information for the exam on Monday as well. 6.022 times 10 to the 23rd is Avogadro's number. And so if we carry that calculation all the way through, I set my calculator down somewhere, but I believe it was 3.9 times 10 to the 22nd atoms of carbon. All right, it's almost 5 o'clock. I promised you till 5. I'll give you one more to go here, just so that I can say that I gave you the full time. Again, from a formatting standpoint, as you're going through this scientific notation, we're looking for the capital E notation. So instead of times 10 to the exponent, put in the capital E and then whatever the value of the exponent is. No spaces in there. It's not looking for that. All right, the equation in question here is the Planck equation. Energy is equal to Planck's constant times the frequency. So Planck's constant, 6.626 times 10 to the negative 34th joules times seconds, multiplied by 6 times 10 to the 10th hertz. Remember that hertz are reciprocal seconds. So the seconds and the reciprocal seconds end up canceling. Put those together to 3 significant figures, 3.98 times 10 to the negative 23rd joules. Now, if you're looking for something that was more in the 10 to the negative 19th range, because that's where most of our other calculations were, yeah, for visible light, that's the range that we worked with. But that light is in the visible spectrum. We are told that this is a microwave. Microwaves are lower energy, higher wavelength light, and so it would only make sense that they are going to be lower energy as well. So this is where we're going to have to end things, unfortunately. If you want, I can edit a couple of questions that are wrong here, give you access to this quizzes. I'll put a link to how to do that in our course Blackboard pages, so that you can access it anytime you want from there. We got through almost all of the questions. The only ones that we didn't were a couple of the calculation questions at the end. That's all I have. Thanks for coming out. Thanks for giving up some of your afternoon here. Most of you I'll see tomorrow. Otherwise, I'll see you on Monday. Have a good day.